Koroush, Shirvan, thank you so much for joining me on the Titans of Nuclear podcast.
All right. Thanks for the invitation, Brett.
Yeah. So you're up at, so you're a professor at MIT. Are you up in Boston right now?
Yeah. I just actually finished lecturing in a course called Nuclear Literacy.
Nuclear literacy?
Yeah.
What's that about?
Yeah, it's the first of its kind, where we have some members of congressional staff, some members of media, as well as think tanks and some advocacy groups there to just learn about nuclear.
Awesome. And before we get to your current work today, I'd love to just kind of take a tour through who you are and how you got into the space.
Yeah, sure. So I actually came from Iran in 2001.
Okay. How old were you then?
I was 14.
All right.
So then me and my family moved to Gainesville, Florida.
And what, in Iran at that time, what was the political circumstances? What did things look like then?
Yeah, I think it was right after 9/11. So there was obviously a start of the big tensions in general between U.S. and Middle East at that time. So it was an interesting time. But the main reason we moved from Iran was for education. My parents really wanted both me and my brother together. They believed they would get a better education in the U.S.
And did they give you any kind of sense as to what might be an interesting field to pursue, or was this just kind of something you kind of cooked up on your own?
Yeah, so once I graduated, I was really interested in math, physics, engineering. As it turns out, my aunt's husband was a professor at University of Florida. There was also another Iranian was the head of the program there.
Specifically in nuclear?
In nuclear engineering, yeah.
Wow. Okay, so you had some familiarity with the field in your family already.
Yeah, I didn't even ask them beforehand, so I wasn't that curious. But they kind of told me, take some classes, and nuclear engineering, believe it or not, has one of the best opportunities in terms of fellowships and financial supports. Yeah. So at the time I applied for these fellowships, that was pretty lucrative, and you get to also, as part of it, go to intern at Southern Nuclear headquarters as an intern. So
that's a big utility, right?
Yeah. And after doing that internship, I was very much interested in the multidisciplinary field that's nuclear engineering, and of course the money also helped a lot to go into it.
So tell me about that, kind of those early days of you learning, what nuclear is, because now you're teaching people. And this was a pretty critical moment in your own personal development. Do you remember some of the things that you were taught, how you were taught, and do you maybe kind of carry those learnings forward into how you think about impressing this knowledge upon the next generation?
Yeah. One of the things, Southern Nuclear they did a lot of their own core designs themselves.
And what does that mean exactly, core design? What are they designing in the nuclear core?
Yeah, so every time they shut down their plants, in this case, they have both PWRs and BWRs. So that's every 18 months for their PWRs and every 24 months for their BWRs. They take about roughly 40% of the fuel, they take it out, put in a spent fuel pool, and then they put new fuels in there. And the arrangement of these fuel assemblies is important in terms of both the performance of the plant in terms of economic efficiency, as well as meeting the required safety technical specifications.
So core design essentially is a specification for enrichment level and position of fuel assemblies, but nobody's redesigning what the fuel assemblies look like or what the physical reactor itself looks like. That's not what core design means.
Yeah. It's mainly positions and coming up with the optimum enrichment patterns and poison distributions and those things.
And is there a name, or is there a different name for when you're designing the actual core? Like, does anyone at Southern or any of these utilities say, actually, forget about the standard, fuel pattern that we've got now. If we bought a bigger vessel or 5 smaller vessels and put them next to each other, we could, have a totally different geometric arrangement. Is there anyone looking at that type of stuff?
So that's a very good question because at that time, especially once I started my graduate work in 2008, the focus changed from what you're talking about, thinking design optimization, to improving predictability. And that's where things like programs like Castle were born, and industry.
And Castle is the Consortium for Advanced Simulation of Light Water Reactors, based out of Oak Ridge.
Yeah. To more accurately predict things. And that's really what last 10, 15 years has been, the R&D in this area has been focused on. But the other important aspect, as you pointed out, is really for a new reactor, let's say now you're not constrained by the vessel size, you're not constrained by the old operating parameters back in the day where, they didn't know how to optimize a steam generator. And so, we set kind of the secondary side pressure based on plant efficiency as well as the perceived safety limits.
What is the secondary side pressure?
So the secondary side pressure right now, it's somewhere in mid-range of 6.5 to 7.5 megapascals, or roughly around 1,000 psi. So about half of pressure of a primary side.
Right, because the primary side for like a standard PWR is something like 2250 psi or something like that, right?
Yeah.
So half. It seems to me like there'd be less stress on the components if you balance the pressure on both sides. How come you don't have 2000 psi on your secondary side, and that way you get better turbine efficiency and less pressure on the heat transfer tubes?
Yeah. So the secondary side, you want the water to boil. So naturally, it has to be lower pressure, because on the primary side, we don't allow the water to boil. So that means the saturation temperature in the primary side gonna be 350 C. So on the secondary side, we definitely have to go to a lower pressure because the primary side is already below saturation. But having said that, as you're kind of alluding to, when newer plants, in fact, if you look at some of the newer Gen 3 Plus plants, you'll see that the secondary pressure side is actually higher than old reactors. And that's why you're seeing efficiencies on the order of 34%, even 35% for light water reactors, versus in the existing generation 2 and 3 plants operating in the US, we're talking about 33%. And a lot of, still to this date, work doesn't go into, optimizing that secondary side. A lot of the small modular reactor concepts out there, some of them went and tried to optimize that. So they were, even though the inherent technology was a pressurized water reactor, they looked at things like if you can do a supercritical cycle on the secondary side or highly superheated cycle on the secondary side. So there was some design thinking there. But in a lot of cases, you see that they just adopt the same parameters as existing power plants, which is, when you have a new plant, might as well try to get as much juice as possible, given the fixed civil infrastructure, which you're paying for.
And why is that? Are you involved in the design of any new reactors, or do you have insight into the design process to maybe help us understand why they just kind of fall back to the same old parameters as opposed to breaking the mold a little bit? And I'm not even saying breaking the mold with new core materials, new fuels, or anything like that, but just kind of rethinking your standard LWR cycle with all of our new knowledge about the operating experience of this fleet for the last 60 years.
Yeah, so I've had work with several vendors, both on PWRs and BWR side, throughout my research career. One of the things the designers, vendors may not want to change is because something is already licensed, the regulator is already familiar with it. So there's a tendency that, let's not touch that, and let's go with what the regulator is, the operating parameters that the regulator is completely familiar with. So that's I would say is probably the main driver of keeping things undone. And there's some good reasons for that. Regulatory cost is a big component when you're thinking about both costs in terms of money as well as time when you're thinking about licensing new designs.
Yeah, I can see that being a big problem. But boy, if it's a hard battle to bring to a regulator just a new secondary side pressure, I just can only imagine what some of the other startups are going through right now with new materials, new reactivity models, the whole thing. It sounds daunting.
Yeah, and a lot of those that type of design thinking where let's try to keep things as simple as possible and not muddy the water with the regulator born out of the 1990s, where terms like inherent safety was born. And in that era, there wasn't the competition wasn't that stiff as today. So in terms of cost. So
you mean in terms of the overall electricity market, competition competing against sources, let's say like natural gas.
Yeah, exactly. So now that competition is much more much stronger. Really, you have to go down and revisit that operating pressure on your secondary side and try to maximize as much as possible.
Just try to eking out any little efficiency. Yeah. So tell me more about that move towards inherent safety, passive safety. Did you track the history of that at all to understand, where these notions came from, why they caught on, why that's the safety pedagogy that we follow? Because there's a lot of potential ways to be safe besides inherent safety or passive safety. For instance, I'm just giving a crazy example. Just like really remote sighting, right? Like, whether you're inherently safe or passive safety or not, if you put it a mile underground, that's another form of safety. Do you know why one has, or can you offer a thesis as to why one pedagogy has caught on over another?
Based on my experience and what I've seen in terms of the trends, when in the 90s, when if you look at academic trends, is usually also an indicator of how healthy is an industry. And you can see the number of students that declare a certain major. You can see it really went down in the 1990s, and because industry was really still suffering from the stigma of 3 Mile Island and dealing with a lot of perceptions regarding its safety performance, and that's where those passive safe designs were born. Especially as the probabilistic risk assessment was becoming more and more of a tool to indicate how safe is a plant.
Something about that doesn't make sense to me, though. So let me throw out a theory, and if you could challenge it, that would be awesome. So the thing that doesn't make sense is, let's say that there are perception issues in the 80s and early 90s. How is making the plant more safe going to fix your perception issues? You know what I'm saying? Like, even if you make it safer, that doesn't mean the public is going to doesn't mean everyone in the public is going to buy a nuclear engineering textbook, analyze what passive safety is, and form their own engineering analysis and then feel confident moving forward, right? It seems like those two things, although they're assumed to be related, public perception and actual safety, it doesn't seem to me like they're related at all, not even one bit. How do we think about that when, if we're trying to solve a public perception issue, engineering our way out of it? I don't get it.
Yeah, I think, it it's goes back to also the underlying theme of this ongoing course here, is that I don't think anyone has come up with a perfect way of communicating risk perception, and so to such way that you can then change people's opinion.
Yeah.
But at the same time, it was believed to be a good measure and good marketing measure to say X plant is 2 orders of magnitude safer in terms of core damage frequency. And
yeah, because
so
everyone in the public knows what core damage frequency
what
is.
is that? Yeah, so therefore, you utility, you should pick me over the other guy. I think it's used as a marketing campaign. But to your point, I agree with that. I don't think anyone has come up with a perfect way of perfect metric to change people's perception.
I've been at some of these meetings where people talk about perception, and when people talk about communication strategy for the nuclear industry. As a matter of fact, I was up at one at MIT 18 months ago or something.
Yeah, I remember that. Yeah.
I think it's when we first met.
Yeah. That's right.
And there's like one voice in the audience that what they said made perfect sense to me, and then what everyone else was saying made no sense to me. And that one voice in the audience was Malcolm Grimston, who's this professor at Imperial College, and when he talks about nuclear accidents, one of the things that he emphasizes is that a nuclear accident, even in its worst case scenario, but let's say for a light water reactor, is no more than a minor industrial accident in like objective terms. And so if we treat it like more than a minor industrial accident, people will perceive it as a huge problem. But if we treat it like a minor industrial accident, people will perceive it like a minor industrial accident. And so, but that ran counter to everything that I've heard otherwise at that meeting and everything that I've heard at other meetings. And so I'm wondering, as you conduct these courses, is there a voice espousing the communication theory that, hey, maybe we should just talk about nuclear like it's not special, like an accident is not that big a deal?
So I've heard that before, even before that workshop, by some people that were advocating that. Again, my still limited experience, especially in today's world where everything is connected, you're always gonna find groups of people that will pick on a particular aspect, and they will basically advocate on that front. Let's say, I don't care if you're saying it's minor, you're probably hiding something, or it could be, So I think in today's world, it's going to be tough. Even if you go by that strategy, it's going to be tough to sell.
Yeah.
But
I guess not coming to a conclusion here, but what are these classes like? Like, what's the debate like when people talk about communication ideology in any given classroom setting about this?
Yeah, I think it's typically formatted. They come with a certain state of mind, so they try to advocate for that state of mind, and it's we try at least try to make it as unbiased as possible. Again, we come up with our state of mind, so I think it's just a good learning opportunity for everyone to kind of at least talk about the subject matter rather than, let's say, convince somebody of anything.
Yeah. Let's come back to your story actually for a little bit. So you studied at Florida for a while, and then you went on to get a master's, PhD. Did you go up to MIT for that?
Yeah.
And what was that like? What's the difference between studying nuclear as an undergrad and studying as a grad student?
Yeah, so the research I was doing in undergrad as well as grad, both of them were pretty applied. Of course, at MIT, you get definitely access to a little bit wider range of both audience as well as experts, being at MIT. With nuclear, because it is a multidisciplinary subject, you to really gain depth in each of those disciplines, it's a slow process. I often think back, and I think if I would do it again, I feel like I even graduated a little bit early from a PhD, and I feel like the 2 to 3 years after the PhD, I feel like I learned also substantially about the depth of nuclear engineering systems.
Like what? What are those topics that you need that extra 2 or 3 years to really master?
Yeah, so even we're talking about the rationale behind some decisions. You kind of when you learn something first, you kind of take it as okay, the truth, and you don't think about immediately like, okay, so then who made that decision? Why did that decision? Why those decisions were made? The other thing is just like with nuclear, just like any industry, in academic world, you get certain information, but that information is typically based on 10 to 15 years old. And as you're aware, with our current existing fleet, especially, we continually upgrade equipment, continually upgrade procedures, and it deals with civil engineering, mechanical engineering, policy, nuclear physics, everything. Yeah, and it takes a little long time to get to gain the necessary knowledge. I feel
it's a complex field, nuclear, right? Because it's like, okay, so not only are you involving pretty much every like mechanical discipline that's in there, but then there's chemistry, and then there's I mean, if you really want to get into the physics part, then you're talking quantum whatever.
Yeah.
And then on top of all that, then you've got like the geopolitical. I mean, it's one of the most geopolitical quandaries that you could imagine. Then there's the economics, as if electricity markets weren't complex enough on their own.
Yeah, exactly.
So I really think that this is the field for, I've said this 100 times. I think the people that I meet in this industry are some of the smartest people I've ever met. And I think that's because you have to be to even start to wrap your mind around all the disciplines that are involved in nuclear.
Yeah, I think it's just if you're there's always things to learn. So that's one thing that definitely this industry.
So what are some examples? Because you mentioned something and that piqued my ears a minute ago when you said trying to understand the justifications for certain design decisions and if they're still applicable. Because when you're told something initially, you just take it at face value. Yeah. But when you look into it, sometimes you find the explanations are pretty pitiful. Like, oh, that's just the way it's always been done, or stuff like that. So can you give me any examples, like specific engineering examples, maybe that you've picked up on throughout the field that you realized were counter to what you initially learned?
Yeah, the first example I guess comes to mind goes back to my internship days, and still is something continually being said that you never put 4 new nuclear assemblies in a PWR together. And it was like, okay, well, then you create a hotspot and everything. But in reality, now we have analysis tools. We have a lot of data that can basically tell us how far are we from those technical specifications. So that's one of those random things that, to me, at least as far as update, I haven't still found a physical justification.
Yeah, that drives me as kind of curious, because I've always wondered when I've learned about fuel shuffling, on each refuel cycle and how they're bringing in some new stuff and some old stuff. I've always wondered, what's it like on your first fuel cycle? Like, don't they all have to be new assemblies?
Yeah. So exactly, and we put poisons, radially distributed poisons, in that first cycle to keep away from the hot spots. Typically, the first cycle in the old days used to be a little bit even more conservative in terms of margins. But you're exactly right. Again, we have that in the first cycle, but then in the later cycles, suddenly, you say, oh, we want to avoid that just because we want to mitigate risks of having hotspots. But now we have, technology that can predict that. So it's things in that general flavor. Why was a assembly designed at 4 meters in height?
Yeah. Why? It seems a little weird, right?
They try to make it as cylindrical as possible because they were worried about neutron economy. You know, if you keep things as square as possible, you reduce leakage. But now, if you look at price of uranium, price of enrichment, it's gone down quite a bit.
So how would you redesign the physical shape of a light water, let's say pressure water reactor, given modern fuel prices? So let's say that neutron efficiency wasn't your biggest concern. Would you make it more elongated? Would you make it more square? What would you do?
Yeah, so the example of it, actually, I did part of my PhD thesis was on the boiling water reactor on that to optimize the geometry of that. And, you know, you got to go back to your objective function. So, so for core design, classically, it was always, you know, you do the reactor physics first, maximize neutron economy and everything. Then you go to your heat transfer, you do your fuel analysis, safety analysis, risk analysis, and then you go to do your economic analysis. But now in today's world, you know, objective function is economics while meeting safety in my mind.
Yeah, that's what engineering should be.
Yeah, exactly. In other fields, that's at least how it's done. Yeah. And so if you go about doing that, and since, you know, neutrons aren't as costly as they were, you know, 30, 40 years ago, what you end up having is a much shorter core with more pins, more tightly, you know, closer together. And that gives you better performance in terms of the economics side of things. And that's
because your vessel can, for any given power density, your vessel can actually be smaller, which means the cost to make the vessel isn't as crazy because it's such a one-off, large, weird thing.
Yeah. You know, you think about the boiling water reactor, the size of the vessel is critical because if the core is shorter, the vessel is shorter, which means the control blades are shorter, which means the space you need to take out the control blades from the bottom of the vessel is shorter, which means that the containment is also shorter, which means the spent fuel, which is in line with the vessel, is also lower elevation. So it's just, you know, it just propagates itself.
I see. So when you talk about how the economics can trickle out of the core, you're actually thinking about the whole building too, and how we can reduce the entire building envelope. Because I mean, that's a big part of the cost, right?
Yeah, exactly. So it has to be integrated manner. Now that we have the two, I mean, you know, other industries do that too now. You know, they've been doing this for decades, where they kind of have an integrated model of the whole system, and then they do design optimization, and you know, vendors do that as well to a certain degree. You know.
Where do these conversations take place? These the conversations of hey, things have changed since the 1970s. Let's say the uranium is the perfect example. How should we be rethinking about designing a nuclear reactor based on the new reality? Does this take place at universities, at the labs, at the DOE? Where are these conversations happening?
I think those conversations happen in a lot of places. You know, for example, on the fuel cost, you know, typically utilities have long-term fuel purchasing agreements, all the way from the ore to enrichment contracts to fabrication contracts. And if on the executive level, the executive in the utility doesn't have the knowledge that these contracts are for 10 years and doesn't have the knowledge that uranium prices have gone down and there could be a possibility they may have, especially with plants being threatening to shut down, they may have some power to redo those contracts. Yeah. Then, you know, then those things that doesn't happen. So it really requires a communication bottom up and top to bottom.
And is there anyone who, we talked about this a little bit before in the episode, how like a nuclear core designer doesn't actually mean that you're redesigning the core. It just means that you're
shuffling,
designing shuffling and fuel enrichment. Where the real nuclear core designers live or work or operate? Who are the people who are actually, you know, putting together a model of a nuclear core where the rods are only 1 meter tall?
Yeah. Yeah, so those would be the people at the vendors, or in nowadays case some startups where they design the core themselves.
The startups are you kind of in touch with the startup community? I mean, a couple of them have probably spun out from classes you've taught, maybe.
Yeah, I'm familiar with the startup scene in nuclear, more or less, with the people. Yeah.
And what do you think? How should we think about the startups? How would you divide them up? Would it be by fuel type? Would it be by how far along they are? How should we think about the nuclear startup scene?
Yeah, I mean it's a tough question to answer. I would say, if you look at the size of the technology they're going after in terms of complexity and required manpower, and maybe divided by the number of people they have, I think that's probably a good metric.
Yeah.
To decide, typical large light water reactor requires millions of man hours of work. And that's that's just data points that we have.
That's a lot of man
so
hours.
if a startup pursuing a large light water reactor and they have 10 people, they're never gonna get there. Obviously, their mission is to get bought out by a vendor, of course. But if you're pursuing a really tiny, microreactor, maybe you can tolerate much fewer
and
people.
What is the difference between a tiny microreactor and a large light water reactor in terms of proof that you have to demonstrate to the NRC? Does the NRC say, oh, if it's small, we're not going to spend this many hours reviewing it, or
yeah? So I mean, it comes back to source term. The first reactor, the CP1, generated 0.5 watt, and if it was being commissioned today, you'll still need a lot more safety precautions that you did in the back of the day. But overall, should be a smooth sailing. 0.5 watt is not much. But if you are reactors generating gigawatts, requires different levels. So microreactor, we're talking about hundreds of kilowatts to maybe 5 megawatts, 10 megawatts at most. So it'll require less stringent process because the source term is less from an NRC point of view.
And source term, for the non-supernuclear audience out there, means in the case of a radioactive release, the source term are those radionuclides that might escape from the reactor.
Yeah, and that's directly proportional to the power, the fission power that the reactor generates.
And how do we model that? Are there models for source term mobility?
Yeah, so to calculate the initial source term, the models are pretty good because that involves knowing neutron cross-section data, as well as half-life of radioactive isotopes, and those are known fairly well within the uncertainty band that you would like. As far as the mobility of it, that's a little bit much harder to predict. So, but if your source term is so low, such that you can do maximum credible release accidents, where you kind of assume, given this thing is in a box, you assume the maximum credible event would be, let's say, like 50% of this just releases out right in the air, and then you can then do the analysis based on some conventional plume modeling and see, does that meet current occupational or public safety limits.
How does that maximum credible release work? How do you prove that, or how do you discern that?
Yeah, so based on kind of known engineering factors, you can basically decide how much of the source term can actually leave, and then you just assume the entire thing just leaves, and again, based on some weather data and some conservative assumptions, you get your.
And are these all custom models that people have to put together themselves, or is there a standard plug and play, like enter in your this and get out that?
Yeah, no. There's a lot of standard models NRC has, DOE has, EPA has. Yeah. I have actually a student working on this front for our fusion friends. His thesis is on fusion regulation, so he has to come up with that source term for the fusion industry.
Yeah, the fusion people don't like to admit that they're NRC regulated also because there's radiation involved.
That's the
they keep
question.
that under wraps for now. Cool. So, one of the things that you've spent a lot of time looking at are small modular light water reactor performance and economics. What are some of the conclusions that you've found by making it smaller? How does that affect economics?
Yeah, some of the work we've done looking at that really says that we have to really do drastic changes in design, similar to what people have. Some vendors are looking at, like a new scale or the Babcocks and Wilcox. I mean, these are reactors that, even though they're pressurized by reactors, the layout does look different than current PWRs. And what we looked at is you have to really go with a very different layout and different methodology in order to be able to be competitive.
And so that's what you found, that layout is what drives your overall cost?
Just in general, it comes down to, because you lose so much from economy of scale, so you'll still need operators, some plant workers, engineering, management. You still have basically the similar, in most cases, worse fuel cost. And then on the capital side, a refueling machine is a refueling machine. Your assembly in a small modular reactor is the same assembly as a large pressurized water reactor. So your refueling machine gonna look very similar, and it takes a lot of, lot of volume, requires a lot of civil structures. Making safety grade pools is extremely challenging, and that's what in general vendors and utilities have found through even recent constructions. So you have to really think differently about the layouts, the auxiliary building, the control room, in addition to the nuclear steam supply system and the turbo machinery side of the island to drive the cost down. Because your battle is to overcome that economy of scale that the large plants have.
Does any of your research, do you guys produce reports where you might actually lay out suggestions for layout design changes? Do you have any drawings that might come out of this work?
So for the nuclear island, there's some published papers. There's a report out there. For the specific the other parts, that's actually an ongoing project. Cool. That's due to finish in May. So we should have a report after that.
Cool. Yeah. One of the things that we always talk about here at the Energy Impact Center, which hosts the Titans of Nuclear podcast, if anyone's confused about those two titles. Yeah. One of the things that we always talk about is just retrofitting coal plants, because coal plants, you've already got your whole balance of plant already built, and they're shutting them down, and those people still want to work. So why not just drop a nuclear core in place of the boiler that they had? Does this come across your guys' plates, and have you thought about how the economics play out there?
Yeah, we looked at it in the past, and I believe there should be maybe even an EPRI study on this front. But from basically looking at it, the issue is the turbine island is not really that big of a cost item. The control systems that go connecting the turbine island to the control building, as well as the the fission side of things, that still needs to be updated. So there isn't a huge economic incentive, other than if for that specific site, there may have been a lot of money spent on site excavation, setting up the switchyard. In some places in the U.S. that can take a couple of $1 billion to do that. So from that point of view, you rather to just use that site because you got the switchyard, you got those things, you got the heat sink. So that's those are the main component that we saw was the main thing that you can reuse. But as far as the turbo machinery, it's first it's low cost, and then you have to really reconfigure it. We didn't really see that much gain.
Yeah. And then advanced nuclear fuel cycles. That's something that you look at, but that also, I'm sure your whole department, is constantly talking about and shuffling back and forth. How do you think about advanced nuclear fuel cycles? And is it always a comparison to LWRs? Light water reactors. Is it always a comparison between advanced and light water reactors? Which is better? Or is it each one is used for a different application? How do we think about the different fuel cycles?
You're referring to basically recycling fuel, is that
or new materials, new fuels altogether?
New fuels, yeah. Okay. The only actually, it's funny because the only reprocessing type of reactor where the reactor would use reprocessed light water reactor fuel or burn reactor fuel. The only design I've actually worked for a long time as part of a long-term project, that reactor actually was a LWR based reactor. It was a reduced boiling water reactor designed by Hitachi as a means to do the recycling of plutonium in Japan. And the way they did it was to boil water as much as possible to actually make the flight time of the neutrons faster to improve the efficiency of disposing plutonium as well as burning nuclear waste. From a point of view of burning and breeding fuel, that just comes back to the cost. To me, that's just come back to the cost issue. Right now, uranium is cheap, so reprocessing from that point of view may not make sense. But also nationally, you may have different objectives. So long-term, let's say, long-term waste disposal, or if you don't like to have a lot of plutonium in your country because that may cause other countries to scrutinize you, then you have to, you want to burn it, and if you want to burn it, you want to burn it efficiently.
But if you have so this is one issue that I think I would like to explore as much as possible because I feel like there's a lot of mixed messages out there in the world. If you have a spent nuclear fuel rod from a light water reactor, isn't it such that your plutonium-240 to plutonium-239 ratio is too high to be used in a weapon?
Yeah, so that's why we call it the reactor-grade plutonium versus a weapons-grade plutonium, where you basically don't have much 240 because 240 is a big absorber. Yeah.
So doesn't that mean that light water reactors are essentially proliferation resistant to a certain extent?
Yeah, and not only that, light water reactor, the conversion ratios is 0.3, 0.4 is already a very good burner for anything. Yeah.
What does that mean? Can you explain a little bit more the ratio there? Yeah.
The conversion ratio is a ratio of the amount of fissile material you start with versus the amount of fissile material you end with. And light water reactors, unlike a lot of fast spectrum reactors, sodium reactors, light cool reactor, they have a very, very low conversion ratio as by default. Now you can make other reactors also low, but the current existing fleet has a very low conversion factor. Means that we're not really breeding efficiently, we're actually burning efficiently. So we are actually reducing, let's say, the footprint.
Walk me through that a little bit more, though. The difference between the burning ratio and the breeding ratio. Can you define those two terms and how they might play out in different reactors?
So breeding ratio and conversion are basically the same thing. So if I had my conversion ratio 1, that means the amount of fissile inventory I started with, I'm going to end up with the same amount of fissile inventory. That means,
and that's good from like a fuel economics standpoint, right?
It's good from a fuel economics standpoint, but of course, when I end up with the same fissile inventory, I sometimes have to go and reprocess that to capture that extra fuel I just spread, to put it in a different location, and that process, obviously, reprocessing, does take some energy and cost. Yeah.
And why is that exactly? Why do they have to reprocess it if it has this high concentration of fissile material still in it? I get, there's some poison accumulation.
Yeah.
But what is the limiting factor on your standard LWR fuel assembly that they just can't leave it in there for a fourth 2-year cycle or a fifth 2-year cycle or a sixth 2-year cycle?
Yeah, because there's a lot of limitations. What you're talking about is we have to increase the burnup, which is the amount of energy extracted per kilogram, in order to continue that incineration waste destruction process. And right now that's limited to a number, it's 62 megawatt days per kilogram. Well, it's a unit of basically how much energy you can extract. And that's limited by uranium dioxide's capability to structurally hold itself. That's limited by the cladding for the 98% zirconium-based metallic cladding to structurally hold itself during accident scenarios. So when you go to a different materials, obviously you may be able to extend that and even burn further. There's also, when you have a low enough fissile inventory, if you want to continue to burn it, you are by definition kind of by the balance of power. Because you want to constantly generate same amount of power, it means that you're relying on other assemblies to generate more power. So you're kind of creating a little bit more hot spots. So then that's limited by your thermal margin, which again are limited by your fuel properties. So let's say in the world of new fuel, you can re-optimize and you can make it basically burn more efficient.
And how come the conversation around reprocessing is always, take it out, do some sort of chemical separation and how come they don't just take the literal pellets, put them in a new cladding, and then just operate it at a lower power? Maybe at a different facility that was designed, you go from a facility that was designed to be 1100 megawatts, bring it down to one that's designed to be an 800 megawatt one. How come they don't do stuff like that?
Yeah, like in the sodium reactor world, they do actually talk about like recladding, because the cladding really becomes limited versus the fuel can take that extra abuse. For uranium dioxide, the pellet pretty much gets pulverized, when you go to 80, 90 megawatt days per kilogram. So it is really, you got to take the dust out and then put it down. And that's, that becomes a little bit impractical. Yeah.
And, I always hear about the sodium or not just the sodium, the fly, the salts, the salts, where they mix in your fuel, but like chemically, like molecularly, it's mixed into your coolant. Is there a scenario where you could have your standard uranium dioxide pellet that, as it becomes pulverized over time, just kind of mixes in, heterogeneously with your coolant, and just kind of, you let that happen. You let there be a powdery solution inside your reactor. Is that a thing? Is that a possibility?
During accidents, once that pulverizes, if the cladding, breaches, the water going to get in and going to take those grains off, and it's going to contaminate the whole system. So as long as you keep the, theoretically, obviously you have, certain dose limits within the primary site outside of the core that if you violate, you have to, shut down. But theoretically, let's say we just keep going. We basically have a granular two-phase flow reactor where we have just uranium components. The first thing that's going to damage is going to be probably your pump seals. It's going to erode. So you're going to start leaking that highly radioactive fuel from there. But there are fuel. It's funny you mentioned it. Just maybe last week, we did a test with an advanced fuel in an autoclave in my lab. And the fuel pellet, which was uranium nitride, became a goo. So we joke that now we can have just a molten fuel reactor in a light water reactor. Because you have basically a goo mixed with your coolant.
Well, you could imagine a light water reactor with a primary loop that there was no cladding at all. You had your pellets just kind of mixed in with the water in some way. And then you just set the vessel geometry such that that's the only place you could maintain criticality. And then the rest of the system where you might have, uranium enter, whether it be a pressurizer or whatever, just wasn't geometrically suitable to maintain a reaction. You could imagine some system like that.
Yeah. I mean, with water, it's a good carrier of solid products. But of course, if you have bulk of the heat generated in water, you have to deal with boiling, and the boiling process will then go ahead and deposit the solid material on the surfaces. So, but again, that's why salt is good, because it then can dissolve it and not boil at those temperatures that we like. I mean, that's what that's why they go with salt. But
yeah.
But it is, theoretically.
I feel like, if we fast forward to 200 years, they're going to be laughing at us at how first nuclear energy wasn't the only source of energy on planet Earth. They're going to be laughing about that. They're going to be like, why did it take them 50, 60, 100 years to figure out that this was the best energy source? So that's one thing they're going to be laughing about. And then they're going to look at, how we just were kind of locked into just one or two ways of doing things. And, this advanced civilization is going to have experimented with 100 different possibilities. I don't know. Whenever I think about the future, it's a future entirely run on nuclear energy.
You're right.
But that's part of your work too. I mean, part of your work is making that future a reality. So how do you think about accelerating innovation in this sector? I mean, I know that's a focus of yours.
Yeah. So what I try to draw is trying to use an integrated approach to any new technology that people smarter than me are proposing to quote unquote save nuclear energy from extinction. And I feel like the integrated approach, where it kind of touches on all the disciplines required for economical and safe deployment of the technology, can really accelerate by kind of taking jump over some of the unnecessary steps, and maybe even remove a couple of these circular cycles that we have when we're talking about new technologies, where we do testing at a very small scale, then we do testing at medium scale, then large scale, then prototypic scale, then final scale. So that's my approach. That's hoping to be able to accelerate, but we do need acceleration of all innovative technologies if you want to live in the 21st century world.
Yeah. And what are some takeaways that you think, if I can encourage you to form a counter narrative, what are some of the things that you think the industry itself, the nuclear industry, not the rest of the world, but the nuclear industry itself has wrong, that you've learned and kind of you want to, espouse or promote a debate amongst the nuclear community itself?
Yeah, that's a tough question. Yeah, I know. Right now, so if I look historically, again, going back to the 90s era, where there was this perception issues and when design came in, and then here comes 2000s, where it's like the Renaissance, and the Renaissance was very profitable era also for utilities, that they made a lot of money, and there was a lot of investments in R&D in nuclear. And you look back and you ask yourself, so why wasn't those funds used to secure the future? That to me, that's the lessons learned. And right now, where there's all these, especially advocacy groups that were anti and now becoming pro-nuclear, and the environmental movement is really spinning out as a bipartisan support in general in Washington. The critical thing, I think, to me is why don't we have a coordinated effort between the government and industry, an industry that has lost a lot of R&D in once the fracking boom took off, and really try to secure the future.
Yeah, it is interesting. And when I say interesting, I mean pathetic, how little effort the industry has put towards securing the future. I mean, when you think about it, every single nuclear plant is like a few $100 million a year operation. These are big companies with a lot of money. And I get it. Yeah, their margins are tight. Okay. But it's still a giant, giant industry nonetheless. Every other industry seems to know how important it is to be investing in its future. And it's almost like the nuclear industry gave up, 50 years ago when they stopped selling new plants. The owners of this, magical technology just didn't have it kind of in their DNA to invest in the next generation. Because now the industry is comprised of what? I mean, yeah, utilities who, a lot of them, the government tells them how much money they can make, or it's just naturally a very conservative industry. You got your waste companies, your decommissioning companies. None of these really care about investing in the future. And that's like all that's left in the industry. So it's troubling. It's troubling.
Yeah. There's also, again, my perspective as an outsider. I'm in a world of academics where we don't have too much accountability, and I can just give you my opinion here. Obviously, a lot of complicated decision making is done, but I feel, as you said, if you look at R&D sector between what was in the nuclear industry, between the utilities versus other industries, I feel like you can see a drastic contrast.
Yeah. Yeah. Sometimes I think that nuclear people are the most afraid of nuclear energy. At least by their actions.
Maybe.
By their actions. All right. So enough of me complaining. As we wrap up here, I would love to kind of hear your optimistic look into the future. If you could kind of tell us what you think, what time scale you think it'll take for nuclear to really, pick up again, and what needs to happen, what's going to catalyze that future vision. Maybe you could, tell us about that.
Yeah, I think, so since you told me to be optimistic, I'll go with that.
That's worse.
Yeah. I think the critical step is, if this perception problem is fixed, the critical step is attracting the best people on civil side, mechanical side, nuclear side, the best people to really invest in the technology and deploy it. Because at the end of the day, I don't think it matters how much concrete, steel, what kind of technology you have. It comes down to project execution and managing your uncertainties. And the only way you do that is if you have the best people that are able to manage group of engineers and workers, welders effectively. And I think you can only get the best when they're actually, are passionate about and they're willing to do this. So I think I'm hoping that will happen. And then once that happens, then you can construct reactors on time and on budget.
Very eloquently put. Koroush, Shirvan, thank you so much for your time today.
All right, thanks a lot for having me.